Hello everyone, welcome to the next session of Strength of Materials. I'm going to solve last two problems on bars with varying cross section or it is being loaded differently at various junctions. So let's read this problem. A rigid bar ACDB is hinged at A and supported in a horizontal position by two identical steel wires as shown in figure below. So these are the two steel wires EC and FD. A vertical load of 30 kN is applied at B, as you can see. Find the tensile forces T1 and T2 induced in these wires by the vertical load. So I have to find T1 and T2, the tensile forces. At end A it is hinged. Here the rigid bar is one word which we need to focus on. The rigid bar means a bar which will remain straight. When you do not apply any load, the bar will remain perfectly horizontal, and when you apply a load like this of 30 kilonewton, A is hinged, so A cannot be displaced down, so A will remain fixed over here and this point B will deflect down, but this deflection which you see will be a linear deflection from A to B end because the bar is rigid. There is another term which we need to focus on, that is two identical steel wires. When I say that these steel wires are identical, I mean to say that their area will be same. Say A1 is the area of steel wire EC and A2 is the area of FD. So they will remain equal. Also the value of Young's modulus will be same. Now length is same, but it is already shown in the figure, so I need not write separately, but this is also the meaning of identical wires had this value not been given, or maybe it would have been mentioned only for as a data. Now let's start with drawing the FBD of this portion. So this is my bar A, C, D, B. When I apply a load of 30 kilonewton, this being hinged, the bar will bend like this. This B will be deformed to a position B dash, D will deform to a position D dash, and C will deform to a position C dash. Let me say this deformation is delta 1 and this deformation is delta 2. Now I am taking delta 1 and delta 2 at these positions because at this end as such I do not have any value to be calculated. In fact, the value is already given here. So if you look at this figure, this is actually a similar triangle and this rigid bar is given, so it will deflect very much linearly. So here I am going to use the linearity theorem, that is delta 1 by delta 2. If you observe, this distance upon this distance will be equal to AC upon AD. Now this distance is given as 1 meter, C to D distance is given as 1 meter. So I have delta 1 by delta 2 equal to AC is 1 and A to D is 2. Or I can say that delta 2 is equal to twice delta 1. So this is my equation 1 that I obtained. The next equation which we are going to use is the extension in this wire EC and in the wire FD. So extension in wire EC is delta 1 will be PL by EA of 1. Now P here stands for T1, L is L1, E is E1 and area is A1. So these are the values that I have taken. Now suppose if I have to calculate the extension in wire FD, which is delta 2, again it is PL upon EA. This is the second one. So here my T will be T2, L will be L2, E is E2 and area is A2. Okay, we have just found a relation that delta 2 is twice delta 1. So this is from equation 1. Therefore T2 L2 by E2 A2 will be twice T1 L1 upon E1 A1. Here L1 and L2 are equal, A1 and A2 are equal, E1 and E2 are equal because the bars are of identical nature. So I have therefore T2 is twice T1. So this is another equation I find. I mark this as equation 2. Now if I take moment about point A because it is hinged, what do I get? T1 will turn anti-clockwise, let me assume that anti-clockwise is positive. So this will be T1 into 1, T2 into 2, and this 30 will be 30 into 3. So suppose if I take summation of moment about A is equal to 0, I take anti-clockwise as positive. This is a pure sign convention. You can change to clockwise being positive. So I'll have T1 into 1 plus T2 into 2 minus 30 into 3 is equal to 0. Therefore, T1 plus twice T2 is equal to 90. I mark this as equation 3. When I solve equation 2 and 3, let's try solving. Therefore, I'll get T1 is equal to 18 kilonewton and T2 is equal to 36 kilonewton, because T2 is twice of T1. Here actually I have substituted T2 is equal to twice T1 and I've got the answer very easily. So I've just written solving 2 and 3. Let's take up another problem. A rigid massless bar AB is supported by two flexible wires AC and BD. You can see this is the massless bar AB. It is supported by two flexible wires AC and BD so that the bar is horizontal in the unloaded state. So currently when there is no loading of this 20 kilonewton, as you see here, it will be horizontal. A load of 20 kilonewton as it is shown here is to be placed at such a point so that extension of each wire is same. This is important. This will help us give a condition to solve the problem. That is, AB remains horizontal. Calculate the position of the load. So I need to calculate this distance x and the force in each wire here and here. The value of E of AC and BD is given. Area of AC and BD is given and length of both the wires have been given. Take distance between wires as 300 mm. There is not 300, it's 3000. As you can see in the figure, 3000. The first thing that I'll do is I'll draw the FBD of it. So I'll draw AB. Then I'll draw this E, which is 20 kilonewton. This distance is x. This distance is 3000 minus x. Now if you look at these fixed ends, suppose if they are removed, then obviously there will be a tension over here of, say the value is, since this is BD, I'll write TBD, and from here if I draw the tension again, it is say TAC, because the wire is A to C, so I'm writing TAC, which is the tension in this wire. Then again this length is given as 2 meter and 5 meter. When I solve this problem, this is the state of unloaded condition. If I apply 20 kilonewton, this bar AB will obviously be deformed. So when it gets deformed, say this is the new deformed condition. This is point B dash and this is point A dash. So this is the change which you see. Let me mark this change or this deformation over here as delta AA dash and the deformation on this side as delta BB dash. If you read the problem, extension of each wire is same, which means delta AA dash is equal to delta B dash. Now delta actually means change in length, I would say deformation is change in length here. So again I'm going to use the formula of PL upon EA. So the value of P is TAC on this side. The value of L is going to be 2000. This length is, it is 2 meter, so it is 2000 mm divided by E. The value of E is 2.1 into 10 raised to 5 from the given data, and the area is given as 50 is equal to, on the other side it is delta B dash, so I'll write TBD into 5000 divided by the value of E is 1 into 10 raised to 5 into area is 75. So all the data that I need is given over here. So I can just take the data from here and solve. So here when I resolve this, I'll get TAC is equal to 3.5 into TBD. This is my first equation. Now next I can use the equation of summation of force in y direction is equal to 0. You will see TAC going upwards positive, TBD going upwards positive, and 20 kilonewton going downwards, so it is negative. So I'll write down summation of force in y direction is equal to 0. Upward I consider as positive. So TAC plus TBD will be equal to 20 into 10 raised to 3. This is my equation number 2. Suppose if I solve equations 1 and 2, I'll get TAC is 1555.56 Newton and the value of TBD is equal to 4 times 4.44 Newton. So these are the values that I obtained. Now I have to calculate the value of x. This is also something I need to find. So if I want to find this value of x, I can use summation of moment about this point E is equal to 0. When I take summation of moment about point E, I have to take moment from the left and right and equate them. So on the left I have TAC into x, and on the right hand side I have TBD into 3000 minus x. Now no positive negative because they are on the either side. So let me take moment about so therefore I have 145.56 into x is equal to 44.44 into 3000 minus x. I get the value of x as 666.66 mm. So with this I end the numericals on stress strain on bars with varying cross section and different loading at various junction. In the next session I will start with some derivation for the loading in tapered bar and how to calculate the elongation in tapered bar. I hope you have understood this lecture. If you have any doubts, write to me in the comment section. Don't forget to like, share and subscribe to my channel. Hit the bell icon for latest updates of my videos. See you in the next session. Thank you.